Swayam Prabha. Digital India. Educated India.
Good morning, gentlemen. So let's continue our discussion on this method of weighted residuals. It's a very important method, and which directly deals the governing equation. And let us just see, just to recall. So we said that the problem can generally be posed as a governing equation here, L phi plus f is equal to 0, where phi is the one which we need to find out. In fact, phi can be a function of xy or may even be xy z. And then it's also associated with m phi plus g, so which is the boundary condition. So that means that this condition need to be satisfied. And so usually this L is a differential operator of higher order and m is a differential operator of a lower order. And then we just talked about this membrane problem. And similarly, we also have discussed the heat conduction problem. So I'm just putting these things, these applications in the framework of putting in this form. So just like this membrane problem, we said that this heat conduction problem also can be put in this manner. Okay. So what we have derived yesterday was the governing equation for phi. Phi is the temperature here. So temperature is our primary variable. And then we went on doing it, and then we had del square phi plus q is equal to 0. So this is the governing equation anywhere in the domain omega. So this has to be satisfied at each and every point p in the domain. So this is the main governing equation, followed by the boundary conditions. So the boundary conditions are of three types. So phi is phi bar. On yesterday we discussed there's something, this boundary can be divided into gamma phi and gamma q and gamma h. So gamma phi is the one where we define the temperature phi, and another type of thing is minus k dou phi by dou n is q bar on gamma q, so which is the heat flux boundary condition. So the amount of heat leaving is defined as q bar. Can even be heat input, then it becomes minus q bar. And then minus k dou phi by dou n is the amount of heat leaving in the direction of n. So n is the outer normal. So then the third one is also related to heat leaving, so which we write it as on gamma h. So this is called convective heat boundary condition, and where the far field temperature is pi infinity. So amount of heat leaving the surface is proportional to that temperature difference, pi minus pi infinity, multiplied by h, which is the convective heat transfer coefficient. Okay, so these are the three types of boundary conditions. So if you want to put it in this framework, okay, in this framework of L phi plus f is equal to 0, so we can identify. So identify here as L is del square and f is q. So that's as far as the governing equation is concerned. Particularly if you take all three are there. So if I just put it the only considering 2 here, then m is minus k dou by dou n. Okay, and then g. So if you take it onto this side, so we can say minus q bar. So this is with regard to the second type of boundary condition. Essentially what I am trying to say is that all these problems, so membrane problem, heat condition problem, they can all be put in this framework. In this, we can pose it in this manner. And in particular, this comes under the class of linear differential equations. And so that means that this, if L is there, so if there are if phi 1 and phi 2 are two functions, so then L phi 1 plus phi 2 can be written as L phi 1 plus L phi 2. So these are the basic. There are many other properties of linear operators, and these come under the class of the linear operator. Okay, so there may be a nonlinear equations for which we also can develop finite elements, but that will have to see it as advanced finite element procedures. Okay, having done this one, so let's look at the solution procedure when the problem is posed in this manner. So our approximate solution procedure. So the approximate solution, what we are saying here is that how do we get phi, which is the exact thing. So we will approximate it as phi hat. So we would like to get an approximation for phi as phi hat here. So we would try to obtain what phi hat will be, and let us say phi hat xy is implied. So what we are going to do is that we are going to put it in the form of, we are going to approximate it as phi 0 so we are going to approximate it as psi naught plus sigma, a summation of terms, n terms as aj psi j. In fact, let me also tell you a little bit more about this one. So psi naught and all these are psi 1 etc. are all functions of, are all known functions, are all known functions. Here we approximate them as some set which has certain important properties. We will talk about that as we go on. So these are all just like we have done it in the case of variational problems. We have assumed x into x minus 1, x square into x minus 1, and x cube into x minus 1 and so on. So a series of functions have been assumed there, and so similarly here, so we assume those kind of functions in a systematic manner. Okay. And why we have separated the psi naught outside here and then psi j's here multiplied by with aj's. So aj's are coefficients. So these are unknown at this moment. Well, if you know it, then the solution is known. So these are unknown coefficients which we have to find out, and we will devise a methodology so how to find out these ages following this, satisfying all these equations, how to satisfy these equations in a best manner. Okay, so this is the approximation which we are assuming in this manner as a linear combination here. So what we need to do is that we have to find out these questions. So, but what about this psi naught and psi j? What is that they are doing here? So what we are trying to do here is that let phi hat whatever satisfy the boundary condition. So as a precondition, we say that we devise this psi naught and psi j's so that phi hat as such will have the satisfaction of this boundary condition. Okay, so what do we mean by this one? So that means that if phi hat is going to satisfy, so what we mean by this one is that, so that means that m times phi hat plus g, so which we write it as m operating on psi naught plus so we can so this is the boundary condition, and so this set psi naught and psi j should be at least chosen in such a manner that this condition is satisfied. So if this condition phi hat I substitute into this one, and if this condition need to be satisfied, so then for any values of aj's, so what we mean, aj's are unknown at this moment, so whatever be the values of aj's, so this equation should be valid, should be equal to 0. So if this has to be 0, then what is that that's necessary? That we need to make this as 0 and we need to make this as 0, right? M operating on psi naught plus g and M operating on psi j has to be 0. So what do we mean by that? So let's write them separately now. So this is on gamma. So if this condition need to be satisfied, is to be satisfied on gamma for any, what will be the values of ages, for any ages, so this has to be satisfied. Then what we need is M psi naught plus G has to be 0 and M psi j has to be 0 on gamma. So these are two things. In fact, this second condition is in fact for all j's going from 1 to n. So this is in fact m psi j being 0 is actually n conditions, and then this is one condition. So this is important part here is that psi naught has been chosen in such a manner that it is going to satisfy the non-homogeneous part of the boundary condition. So there is a g is there, so this has to be 0, right, with a g. So knowing g, so psi naught should be chosen in such a manner that this is satisfied, and similarly psi j's had to be satisfied such that m psi j is 0 on gamma. Okay, just as an illustration, for example, if you have this heat condition problem, let us say if you have gamma phi, where phi is written as phi bar on gamma phi, then if this is the kind of thing which need to be satisfied, so if you want to make a choice, so what is that which we have to do? So phi hat, if you are putting it as this, to go through this procedure, so we should say that then psi naught has to be equal to phi bar on part of the boundary condition on gamma phi. And what about psi j? Psi j has to be 0 on gamma phi. So these are the, looks a little peculiar, but then you will appreciate that by assuming these things in this manner, so then the phi hat is going to satisfy the boundary conditions for any set of these coefficients ages. So that is the important part. Okay, so the important part is that whatever the values of ages here, so this phi hat is going to satisfy the boundary condition. Okay, so that's what we have done so far, is that we made a choice of this phi hat and which satisfies the boundary condition, right? So out of this, so this is satisfied, the boundary condition is satisfied for any set of ages, and then that leaves this governing equation that need to be satisfied. So how do we do that? So that will be satisfied in an approximate sense. So that means that now, so we are left with, so that leaves the satisfaction we need to satisfy the governing equation. Governing equation in omega. So what we need to do, what I mean is that, so this has been satisfied. So m phi hat plus g has been satisfied for any set of ages, but what is left out is that L phi hat plus f. So we want to make it 0. If this is satisfied, so that means that the whole problem is satisfied, and then that will be the solution. But however, we know that the sets which we have chosen, psi naught, psi j and all that, they are not the exact solutions. So there are only some known functions, but then we have to make a choice of ages so that we get the best approximation. We will see what is that best approximation. So we need to make this 0. So we know that it is not going to be 0. So then there is an error in this one. Okay, so this is not equal to 0. So this is the, so there is an error here. So what we say here, L phi hat plus f is non-zero, and we call this as, instead of error, the mathematical term that's used is the residual. So this is called the residual error. So if it's the residual, so something is left out, so we call it as residual or error, and our task is to make this residual as small as possible, okay, in the best possible manner. So if you want to make this as 0, then the thing is that if you just make it 0, how do you make it 0? So to make it 0, there are several procedures. You can make it in an integral manner, okay. So but then this error, you can say that I'm going to integrate it over the whole domain omega, and then I'll set it equal to 0. But what is the problem with that? The problem with that is that it is going to give you just one equation, whereas we have n coefficients, and so we need n equations. So how is that possible? So the procedure here is that, so instead of simply saying integral r being 0, so what we say here, so we make r 0 in a weighted manner. What is weighting? So that means that this r is being multiplied by wi. So wi itself is a known function, so let us say of xy, and then so you are multiplying this residual with the weighting function here. You call it magnification factor, or you call it as a weighting factor. It's a function, it's a known function. So that means that if it is equal to 1, so that means that you are giving weightage equal, or if it is not equal to 1, then you are giving some special extra weightage or residual in certain use. So I'll just explain it to you. Okay, so this is the equation. So you are multiplying, so you can also say that we'll continue this here. So phi hat, we can write it as L psi naught plus Aj L psi j and plus F is equal to integrated over the domain omega. D omega is dx dy. You can write it dx dy, or for the moment we'll write it as d omega. So the important part here is that, so this is an equation here. So what is this equation? So this equation is one knowing wi. So this is going to give one equation. So knowing wi, we get one equation, call it linear equation in ages. So that means that because this is a1, a2, a3 are all there, so the rest of the functions are known. So we assume that the integration can be done. So this is one equation we will get in terms of ages, right? a1, a2, an. But then we still have n coefficients and we need n equations. So how do we get n equations? So we get n equations by making different choices for this weighting function. So by choosing weighting functions, say n different types of weighting functions, so you get n equations. So we are going to talk about this a lot more. So by choosing different wi's, say n, we get n simultaneous equations. So these are all algebraic equations. Algebraic. So theoretically, so it's very clear. So choosing the weighting function, for each weighting function we get one linear equation, and if you have n weighting functions, you will get n algebraic equations. So just to explain a little bit more, what is this weighting function? Is that, what is this? Just a little bit. One thing is that, so if you choose, so if this is R, so what is the importance of this weighting function? So the weighting function, for example, let us just say it is a small function here and over a small domain here. We have a value of Wi is equal to 1. So what is that? This residual is being multiplied with, let us say Wi being 1. It can even be not necessary that like this, it can even be some function like this. So I have just chosen this one, a step function, just to simplify the explanation. So if you multiply these two, so what is that which we are going to get here is that, so this is 0 here, and just 1 here. So means that, so what you are going to get is so what interesting part here is that though the residual is like this one, but by multiplying with this weighting function equal to 1, so what you get is a product of these two, which looks like this one, a brown thing, right? So what it means is that the whole product here is just the integration of this brown line. So this is what we mean by giving weightage or giving magnification. So that means that the whole residual, when you take the integral, is nothing but only the integral of this part. So like this, you can have different weighting functions. Let us say for this one, here and here and here, wherever you want, W1, W2, W3. So using these kind of weighting functions, so we have the integration of residual. So what is that finally you infer? So you can very well see that by taking these small stepwise weighting functions, so you are making the residual here, this integration to be 0, and you are making the integration of the residual here 0, and here 0, and here 0. So that means that if you have n such things, n tending to infinity, so you are making the residual, that is the error, being 0 all over the domain omega. Okay, I hope you got this picture. And so that is that part. And let's try to understand what is this. Still it's not very clear for us. Let us try to understand it from the vector mechanics point of view. I mean vectors point of view, vector algebra point of view. Okay, so let us just see here what do we mean by that. From vector algebra, explanation from vector algebra. So let us say that we have a three-dimensional thing, and let us say that we have a vector here, we call it as R. So R here, say it is Rx, like this one, right? So let's assume that we have an unknown vector R here with 3 components in x, y, z. And so if you insist that this R multiplied by I has to be 0, so what does this mean? So this vector R here taken a product with I, dot product with I, so it means that it is nothing but, what is that? The component of R in the direction of x-axis, right? Or you can even say that the component of, so this is nothing but component of R in the x-axis, so that is what R dot I, and that is going to be 0. So this is the condition. So so that means that if you make this condition, so it shows that its component along x-axis is 0, right? And so similarly, so which means puts a condition that R should not be having any component in the x-axis. So the same thing if you continue, saying that its component along y-axis is 0, its component along k along z-axis is 0. So that means that what will be the R? So R has 0 component in x-axis, 0 component in y-axis, 0 component along z-axis. So this has to be 0. So if you put a condition, these three conditions if you put it, so what will be the value of R? R has to be 0 by itself, right? R cannot have a component here in x-axis, R cannot have a component in the y direction, R cannot have a component in the z direction. So its dot product along x-axis, y-axis and z-axis, if there is 0, so then it is nothing but it has to be identically 0. So this is as far as the finite dimensions algebra is concerned. In fact, this is called a projection of R along x-axis, right? This is the projection of R along y-axis, and this is the projection of R along z-axis. So that is exactly what we are saying here. In the functional space, so what we are saying here is the projection of R along the function Wi. Okay, this is the called inner product. So the projection of R along the function Wi is 0. So if this Wi is n terms, n tending to infinity, so that means that R projection along all these functions is 0, just like we are saying here. So the projection of R along all these functions, it is 0. So if this W itself is a set of functions, okay, by which we can construct any general function. So if it is 0 along all those functions, so then R has to be 0 in total, right? Its projection along W1 is 0, its projection along W2 is 0, its projection along W3 is 0. So if it is projection of R along all these functions, if it is 0, so that means that R itself is 0 in a total sense. Okay, I think we'll stop here. We'll continue our discussion, and we'll also see how this can be applied to get the solution. Okay, bye bye.